In mathematics, the matrix exponential is a matrix function on square matrices analogous to the ordinary exponential function. Abstractly, the matrix exponential gives the connection between a matrix Lie algebra and the corresponding Lie group. Let X be an now, n real or complex matrix. The exponential of X, denoted by X or exp, X, is the now, n matrix given by the power series. The above series always converges, so the exponential of X is well defined. If X is a 1A, 1 matrix, the matrix exponential of X is a 1A, 1 matrix whose single element is the ordinary exponential of the single element of X. Properties: let X and Y be now, n complex matrices and let A and B be arbitrary complex numbers. We denote the now, n identity matrix by A and the zero matrix by 0. The matrix exponential satisfies the following properties: EO equals I, EA sub X equals E, A plus B, X, X equals I. If xy equals yx, then exey equals ex equals e, x plus y. If y is invertible, then exy1 equals exir1, exp, xt, equals t, where xt denotes the transpose of x. It follows that if X is symmetric, then X is also symmetric, and that if X is skew-symmetric, then X is orthogonal. exp, zab, equals a, where zab denotes the conjugate transpose of X. It follows that if X is Hermitian, then X is also Hermitian, and that if X is skew-Hermitian, then X is unitary. Linear differential equation systems. One of the reasons for the importance of the matrix exponential is that it can be used to solve systems of linear ordinary differential equations. The solution of, where A is a constant matrix, is given by. The matrix exponential can also be used to solve the inhomogeneous equation. See the section on applications below for examples. There is no closed-form solution for differential equations of the form where A is not constant, but the Magna series gives the solution as an infinite sum. The exponential of sums, for any real numbers x and y, we know that the exponential function satisfies x plus y equals xi. The same is true for commuting matrices. If the matrices x and y commute, then. However, for matrices that do not commute, the above equality does not necessarily hold. In this case, the Baker-Campbell-Hausdorff formula can be used to calculate x plus y. The converse is not true in general. The equation x plus y equals xey does not imply that x and y commute. For Hermitian matrices, there are two notable theorems related to the trace of matrix exponentials. Goldini-Thompson inequality. If A and H are Hermitian matrices, then note that there is no requirement of commutativity. There are counterexamples to show that the Goldini-Thompson inequality cannot be extended to three matrices and, in any event, TR, exp, A, exp, B, exp, C is not guaranteed to be real for Hermitian A, B, C. However, the next theorem accomplishes this in a way. Lieb's theorem, the Lieb's theorem, named after Elliot H. Lieb, states that, for a fixed Hermitian matrix H, the function is concave on the cone of positive definite matrices. The exponential map. Note that the exponential of a matrix is always an invertible matrix. The inverse matrix of X is given by AX. This is analogous to the fact that the exponential of a complex number is always non-zero. The matrix exponential then gives us a map from the space of all now, n matrices to the general linear group of degree n, that is the group of all now, n invertible matrices. In fact, this map is surjective, which means that every invertible matrix can be written as the exponential of some other matrix. For any two matrices X and Y, where AAA denotes an arbitrary matrix norm, it follows that the exponential map is continuous and Lipschitz continuous on compact subsets of Mn, C. The map defines a smooth curve in the general linear group which passes through the identity element at t equals 0. In fact, this gives a one-parameter subgroup of the general linear group, since the derivative of this curve at a point t is given by the derivative at t equals 0 is just the matrix X, which is to say that X generates this one-parameter subgroup. More generally, for a generic t-dependent exponent, x, t. Taking the above expression x, t, outside the integral sign and expanding the integrand with the help of the Hadamard lemma, one can obtain the following useful expression for the derivative of the matrix exponent. The determinant of the matrix exponential, by Jacobi's formula, for any complex square matrix the following trace identity holds. In addition to providing a computational tool, this formula demonstrates that a matrix exponential is always an invertible matrix. This follows from the fact that the right-hand side of the above equation is always non-zero, and so det EA, a permel 0, which means that EA must be invertible. In the real-valued case, the formula also exhibits the map to not be surjective, in contrast to the complex case mentioned earlier. This follows from the fact that, for real-valued matrices, the right-hand side of the formula is always positive, while there exist invertible matrices with a negative determinant. Computing the matrix exponential, finding reliable and accurate methods to compute the matrix exponential is difficult, and this is still a topic of considerable current research in mathematics and numerical analysis. Both MATLAB and GNU Octave use PARDA copyright approximant. Several methods are listed below. Diagonalizable case: if a matrix is diagonal, then its exponential can be obtained by exponentiating each entry on the main diagonal. This also allows one to exponentiate diagonalizable matrices. If A equals U dual 1 and D is diagonal, then EA equals UE dual 1. Application of Sylvester's formula yields the same result. Projection case: if P is a projection matrix, its matrix exponential is EP equals I plus P. This may be derived by expansion of the definition of the exponential function and by use of the idempotency of P. Rotation case: for a simple rotation in which the perpendicular unit vectors A and B specify a plane, the rotation matrix R can be expressed in terms of a similar exponential function involving a generator G and angle I. The formula for the exponential results from reducing the powers of G in the series expansion and identifying the respective series coefficients of G2 and G with a cos I and sin I, respectively. The second expression here for EGI is the same as the expression for R I in the article containing the derivation of the generator R I equals EGI. In 2 dimensions, if and, then, and reduces to the standard matrix for a plane rotation. The matrix P equals a G2 projects a vector onto the A plane and the rotation only affects this part of the vector. An example illustrating this is a rotation of 30 a degree equals I/6 in the plane spanned by A and B. Let n equals I of P, so n2 equals n and its products with P and G are 0. This will allow us to evaluate powers of R. Nilpotent case: a matrix N is nilpotent if nq equals 0 for some integer q. In this case, the matrix exponential n can be computed directly from the series expansion, as the series terminates after a finite number of terms. Generalization: when the minimal polynomial of a matrix X can be factored into a product of first-degree polynomials, it can be expressed as a sum. Where A is diagonalizable, n is nilpotent, A commutes with n. This is the Giordani-Chevalier decomposition. This means that we can compute the exponential of x by reducing to the previous 2 cases. Note that we need the commutativity of a and n for the last step to work. Another method if the field is algebraically closed is to work with the Jordan form of x supposed that x equals pjpa1 where j is the Jordan form of x. Then, also, since, therefore, we need only know how to compute the matrix exponential of a Jordan block. But each Jordan block is of the form where n is a special nilpotent matrix. The matrix exponential of this block is given by evaluation by Laurent series. By virtue of the Cayley-Hamilton theorem, the matrix exponential is expressible as a polynomial of order n1. If P and Qt are non-zero polynomials in one variable, such that P, A, equals 0, and if the meromorphic function is entire, then. To prove this, multiply the first of the two above equalities by p, z, and replace z by a. Such a polynomial Qt, z, can be found as follows. See Sylvester's formula. Letting a be a root of p, qa, t, z, is solved from the product of p by the principal part of the Laurent series of f at a, it is proportional to the relevant Frobenius covariant. Then the sum street of the qa, t, where a runs over all the roots of p, can be taken as a particular Qt. All the other Qt will be obtained by adding a multiple of p to street, z. In particular, street, z, the Lagrange-Sylvester polynomial, is the only Qt whose degree is less than that of p. Example, consider the case of an arbitrary 2 by 2 matrix. The exponential matrix ether, by virtue of the Cayley-Hamilton theorem, must be of the form. For any complex number z and any C algebra B, we denote again by z the product of z by the unit of b. Let I plus or minus and I squared be the roots of the characteristic polynomial of a. Then we have. And hence, if I plus or minus a permil I squared, while, if I plus or minus equals I squared, so that, defining, we have, where sin, Qt/Q is 0 if t equals 0, and t if q equals 0. Thus, as indicated above, the matrix A having decomposed into the sum of two mutually commuting pieces, the traceful piece and the traceless piece, the matrix exponential reduces to a plane product of the exponentials of the two respective pieces. This is a formula often used in physics, as it amounts to the analog of Euler's formula for Pauli spin matrices, that is rotations of the doublet representation of the group SU, 2. The polynomial street can also be given the following interpolation characterization. Define A, Z, A permil S, and N A permil DEGP. Then street, Z, is the unique degree n polynomial which satisfies street, K, A, equals A, K, A, whenever K is less than the multiplicity of A as a root of P. We assume, as we obviously can, that P is the minimal polynomial of A. We further assume that A is a diagonalizable matrix. In particular, the roots of P are simple, and the interpolation characterization indicates that street is given by the Lagrange interpolation formula, so it is the Lagrange-Sylvester polynomial. At the other extreme, if P equals n, then the simplest case not covered by the above observations is when with A permil B, which yields evaluation by implementation of Sylvester's formula. A practical, expedited computation of the above reduces to the following rapid steps. Recall from above that an n by n matrix exp, tar, amounts to a linear combination of the first n1 powers of A by the Cayley-Hamilton theorem. For diagonalizable matrices, as illustrated above, for example in the 2 by 2 case, Sylvester's formula yields exp, tar, equals b plus or minus exp, t plus or minus plus b squared exp, t squared, where the bs are the Frobenius covariants of A. It is easiest, however, to simply solve for these bs directly, by evaluating this expression and its first derivative at t equals 0, in terms of A and I, to find the same answer as above. But this simple procedure also works for defective matrices, in a generalization due to Buchheim. This is illustrated here for a 4 by 4 example of a matrix which is not diagonalizable, and the Bs are not projection matrices. Consider, with eigenvalues I1 equals 3 over 4 and I2 equals 1, each with a multiplicity of 2. Consider the exponential of each eigenvalue multiplied by t, exp, I it. Multiply each such by the corresponding undetermined coefficient matrix B. If the eigenvalues have an algebraic multiplicity greater than 1, then repeat the process, but now multiplying by an extra factor of t for each repetition, to ensure linear independence. Sum all such terms, here for such. To solve for all of the unknown matrices B in terms of the first three powers of A and the identity, we need four equations, the above one providing one such a t equals 0. Further, differentiate it with respect to t. And again. And once more. In the general case, now one derivatives need be taken. Setting t equals 0 in these four equations, the four coefficient matrices Bs may be solved for, to yield. Substituting with the value for A yields the coefficient matrices. So the final answer is. The procedure is quite shorter than Pugh's algorithm sometimes utilized in such cases. Illustrations: suppose that we want to compute the exponential of. Its Jordan form is. Where the matrix P is given by. Let us first calculate exp, j. We have the exponential of a 1A, 1 matrix is just the exponential of the one entry of the matrix, so exp, j1, 4 equals A, E4. The exponential of j2, 16, can be calculated by the formula E, i.e. plus an, equals an mentioned above. This yields. Therefore, the exponential of the original matrix B is. Applications: linear differential equations. The matrix exponential has applications to systems of linear differential equations. Recall from earlier in this article that a homogeneous differential equation of the form has solution e to y, 0. If we consider the vector, we can express a system of inhomogeneous coupled linear differential equations as making an ansatz to use an integrating factor of a at and multiplying throughout, yields. The second step is possible due to the fact that, if AB equals BA, then E at B equals BEat. So, calculating EAT leads to the solution to the system, by simply integrating the third step in TS. Example: consider the system. The associated defective matrix is. The matrix exponential is. So that the general solution of the homogeneous system is. Amounting to. Example: consider now the inhomogeneous system. We again have. And. From before, we already have the general solution to the homogeneous equation. Since the sum of the homogeneous and particular solutions give the general solution to the inhomogeneous problem, we now only need find the particular solution. We have, by above. Which could be further simplified to get the requisite particular solution determined through variation of parameters. Note C equals IP, 0. For more rigor, see the following generalization. Inhomogeneous case generalization, variation of parameters. For the inhomogeneous case, we can use integrating factors. We seek a particular solution of the form IP, t, equals exp, tar, a euro zar euro, t, a euro. For IP to be a solution. Thus, where C is determined by the initial conditions of the problem. More precisely, consider the equation. With the initial condition y, to, equals yo, where A is an n by n complex matrix, f is a continuous function from some open interval I to an, is a point of I, and, is a vector of an. Left multiplying the above displayed equality by A tar yields. We claim that the solution to the equation with the initial conditions for 0 per mole currency K, n is, where the notation is as follows, is a monic polynomial of degree n greater than 0, f is a continuous complex-valued function defined on some open interval I, is a point of I, is a complex number, and, sk, t, is the coefficient of n. The polynomial denoted by n subsection evaluation by Laurent series above. To justify this claim, we transform our order n scalar equation into an order 1 vector equation by the usual reduction to a first-order system. Our vector equation takes the form where A is the transpose companion matrix of P. We solve this equation as explained above, computing the matrix exponentials by the observation made in subsection alternative above. In the case n equals 2 we get the following statement. The solution to is where the functions SO and S1 are as in subsection evaluation by Laurent series above. See also. References: Horn, Roger A. Johnson, Charles A. Topics in Matrix Analysis. Cambridge University Press. ISBN A978-0-521-46713-1A. Moeller, Cleve. Banlone, Charles F. 19 Dubious Ways to Compute the Exponential of a Matrix, 25 years later. Siam Review 45, 3 €49 doi, 10.1137 per second 00361445024180. ISNA 1095-7200A. Suzuki, Majuo. Decomposition formulas of exponential operators and Lie exponentials with some applications to quantum mechanics and statistical physics. Journal of Mathematical Physics 26, 601 doi, 10.1063/1.526596. Curtright, T.L. Fairley, D.B. Zachos, C.K. A compact formula for rotations of spin matrix polynomials. Sigma 10, 084 doi, 10.3842/Sigma. 2014.084. External links, Weierstein, Eric W., Matrix Exponential, MathWorld. Module for the matrix exponential.